Welcome to AP Physics 2 Cram videos. We're still talking fluid dynamics here. So we have starting off with a siphoning tank here. I've got a tube that goes up and around like this. And of course it comes down here. Okay, and let's say this is water. So water has a density of 1,000 kilogram per meter cubed. And the question is, what's the maximum height that this tube can be such that we can still siphon water? Okay, well, assuming that the pressure is 101,300, the way we can find that is just say pressure equals rho GH. Rho being that density, G being the gravity, and H being the height. Okay, so height would then be calculated above, okay, based on these two, and then just divide those into there, and then of course add 8 to it. So our height would then be from the surface of the water up to a max height, and of course add 8 because we're starting the surface that's 8 meters already above the ground. So that's how you can find that. In other words, the question is really asking how high of a water column can atmosphere push down and make water go up. Because at the surface, the hydrostatic pressure, or the pressure, is just due to the atmosphere pushing down. So the atmosphere pushes down, forcing water up the tube. And as long as the end of your siphoning tube is below this tube here, water will come out. And of course, you got to make sure there's no air bubbles in there, because air bubbles will stop the siphon from happening. Okay, let's move on. What about Pascal's principle? Well, Pascal's principle states that force 1 over area 1 equals force 2 over area 2. So how does it work? Well, it works, it's hydraulics. What you do is you have a skinny pipe over here with a fluid that fills all the way here up to there. And when you push down with force 1, because the area is larger here, you can hold up another object that has a much greater mass or weight. Now, Pascal's principle says any force applied here goes undiminished throughout the fluid. So whatever force you are putting on the water here, it's going to be force per unit area, so there's going to be a pressure. So that pressure is going to go all the way through here and then push on this. And because the area is different here, you're going to have a different force that's going to be able to be held up. So this large right here, 18,000 newtons, is not going to take anywhere near as much pushing down here because this is such a small pipe versus a larger pipe there. So that's how Pascal's principle works. Next, the continuity equation for flow. It goes like this: A1 V1 equals A2 V2. Now flow, or the flow rate for a fluid going through a pipe, is then equal to area, times velocity. Well, area is meters squared, and if we multiply that by a meter per second, what flow rate really is a volume, per time. So we have a wind tunnel here. If air enters this direction here, and it's going to come out this side here, well, what happens is the radius is getting smaller and smaller and smaller here in the middle here. So let's take a look at this point right here. Well, the volume flow has to be the same everywhere, otherwise you would get like null space in there, which doesn't make any sense. So if we look at this equation here, we've got an area here and a volume here. If area happens to go down, then velocity has to go up in order for the volume to stay the same. And vice versa. And this is how wind tunnel works. You got fans that bring air in, then the pipe gets smaller, and the velocity has to go up in order to keep this continuity equation valid, because flow rate has to be the same everywhere in there. You might notice it when you walk into a tunnel, you feel that air is moving faster in the tunnel already, so when you get in there. All right, now what about Bernoulli's equation? Okay, so if I have something like this, I've got an A1 here and an A2 here. Bernoulli's equation looks like this. Let's call this the initial condition where air or fluid is entering here, and we have air or fluid entering out this side here. So it goes like this. Pressure 1 plus 1/2 rho v squared plus rho gh. Okay, and we probably should put 1s here and 1s here also. Must equal the pressure 2 plus 1/2 rho v2 squared plus rho gh 2. Okay, and this is really the law of conservation of energy as it applies to laminar flow or flow of a fluid. So a fluid enters here at this particular location, this particular height. The pressure outside here, or the pressure of the fluid at that instant, depending on what's going on, can be recorded. A beginning velocity recorded here and beginning height, and you fill in all that information here. It then goes up, so there could be a second pressure here of the fluid. If it's outside, it could be atmosphere. And then plus 1/2 rho v squared, how fast it's traveling there, plus rho gh2. So we can use this equation to solve for any one of these variables depending on what information is given in the question. But one variable will be unknown. But one thing to point out though, the area here in velocity 1 and area 2 in velocity 2, you can still find that by using the equation A1 V1 equals A2 V2. So as long as I know area 1 and velocity 1, and I know my area 2, I could still find my velocity 2 at the very top. So then I can plug in information, and then you're probably trying to find pressure 2 at the top then when it reaches there. So that's how you can use those to determine some kind of flow. Bernoulli's equation is useful for lots of reasons. Okay, some of the physics of flight, for instance, is really important. So as air approaches a wing like this is a wing of a plane looking at it from the side view. We have air must go around this way. And then air goes this way. Okay, well, there's a greater distance that the air has to go through versus the air on the bottom. And again, flow rate has to be same. So the velocity here we'll call velocity 2. And we'll call this one velocity 1. So the velocity 2 must be greater than velocity 1. And you're going to find out that their pressures are inversely proportional to velocity. So let's call this one pressure 1 and this one here pressure 2. Okay, so what that means then is if we look at this here, pressure 2 is actually going to be less than pressure 1. So that will cause lift on the wing. It'll push it upwards like this. So that's one of the reasons why there is lift on a wing. There are other reasons as well. And that'll do it for now. Video 3 will be coming up soon. Hopefully that's making good sense. And we'll have another video out soon.